Sometimes we have a couple of vectors inside of a vector space, and we ask, what's the smallest subspace that contains these vectors? That space is called the span of those vectors. So if we're given vectors, let's say v1 through vn, inside of some vector space V, we define span of v1 through vn to be the smallest subspace of V containing v1 through vn. Equivalently, this is the set of all C1 V1 plus C2 V2, the set of all real linear combinations of those vectors. So they'll necessarily be in the vector space, because the vector space is closed under scalar multiplication. So if you multiply one of these by a scalar, you're still in the space. And then the vector space is closed under addition. So all sums of this form will still be in the vector space. So these expressions are definitely in that vector space. They might even end up describing the whole vector space, or they might describe something smaller inside of the vector space. So for example, in real 2 space, the span of, let's say, just one vector AB is the line containing all multiples of AB. It's a line assuming A and B are not both 0. If A and B are both 0, the span of the origin is just the origin. No matter what linear combinations you take of the origin, you just get the origin back again. So we've got this vector AB. The span is all possible multiples, so it's a line to the origin. So it passes through the origin 0, 0 because one of the multiples of AB is 0 times AB, and 0 times AB is the origin. Now if we have 2 vectors in R2, we wonder what they span. Assuming they're not 0, they could either span all of R2 or they could just span a line. So let's say we have AB and CD. Let's say these are non-zero points in R2, or vectors in R2 if you like. What is the span of AB and CD? Well, for one thing, if CD is a multiple of AB, then we just have the line all multiples of AB again. Now I claim that if CD is not a multiple of AB, then the span of these two vectors is all of R2, the whole real plane. So the reason is, if CD is not a multiple of AB, then the parallelogram that we get by putting one arrow to AB and one arrow to CD then this parallelogram has non-zero area. If CD were a multiple of AB, then it would sort of collapse to be a degenerate parallelogram. It would just be a line. But if CD is not a multiple of AB, then they point in, the two vectors point in different directions, and we get an actual parallelogram with some non-zero area. Now this area is the absolute value of the determinant of the matrix whose columns are A, B, and C, D. So if that parallelogram has non-zero area, that means that the determinant is not zero. Then that means that the system of equations A, B, C, D, x1, x2 equals any right-hand side you want, let's say R1, R2, has a solution for all values of R1 and R2. So if this has a determinant that's not zero, that means we can invert that matrix. And the solution is x1, x2 equals A, C, B, D inverse times R1, R2. So no matter what numbers we plug in for R1, R2, we can solve for x1 and x2. So if this has a solution, we can break up this matrix and rewrite this as, so the system can also be written as x1 times AB plus x2 times CD equals R1, R2. So we just said that for any R1 and R2 we can solve this equation for x1 and x2. That means that any point R1, R2 in the real plane can be written as multiple of AB plus multiple of CD, which is the definition of spanning. If we can write any element of the vector space as a linear combination of these two things, then these two span it. So if we have two vectors in R2, you could just make a matrix out of them, take the determinant. If it's not 0, then they span R2. So if determinant of A, B, C, D is not 0, then A, B, and C, D span R2. Now R3 is similar. If we're given, let's say A1, A2, A3, B1, B2, B3, C1, C2, C3, these span the whole space R3 if the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3 is not 0. Otherwise, they could span a plane in R3, which will necessarily go through the origin. Because 0 times this plus 0 times that plus 0 times the third thing is the origin. Or a line also through the origin. And they would span a line if they're all multiples of the same vector. So they span a line only if all are multiples of the same vector. For example, something like 1, 0, negative 2, negative 1, 0, 2, 3, 0, 6. Since these are all in the same line, the only thing we can get by taking linear combinations of them is more points on that line. All right, let's look at vectors in other vector spaces. So let's let M2R, again, be the space of real 2x2 matrices. So let's ask, what is the span of the identity and the matrix that has ones off the diagonal and zeros on the diagonal? Well, it's all the matrices we can get by taking a multiple of this plus multiple of that. So taking a multiple of the identity is going to put, let's say we take A times the identity, that's going to put A on the diagonal. Then if we take B times this matrix, that's going to put B off the diagonal. So it's all the matrices you can get by putting one number on the diagonal and another number off the diagonal. Similarly, if we look in the space of 3 by 3 matrices, what is the span of I'm going to put a bunch of matrices here. I'm going to put 6 of them actually. So we've got a 1 in position 1, 1, 2, 2, then I'm going to write a matrix with a 1 in position 3, 3 only. And then a position 1 in position 1, 2, a 1 in position 2, 3, and finally a 1 in position 1, 3. So what is the span of these 6 matrices? Well, if we take linear combinations of them, multiple of this plus multiple of that plus multiple of the third one, etc., then we're going to get the coefficients of the linear combination right in the position where there's a 1 in that matrix. So it's all the matrices of the form A times this first one times B times the second, plus B times the second, plus C times the third, plus E times the fourth, plus F times the fifth, plus G times the sixth. So it's all the matrices we can get by putting numbers in these entries where those numbers could be anything that's real. So this is the space of upper triangular matrices. Another example. In the complex numbers, what is the real span? I'm just saying real to emphasize that I'm taking real linear combinations of 1 and I. So I is the number, the imaginary number that satisfies I squared is -1. So it's all multiples of 1 plus all multiples of I. All real multiples of 1 plus all real multiples of I, which is the same as saying all real numbers A plus all real multiples B of I, where A and B are real. So it's all the complex numbers, because every complex number can be written as real plus real times I. Similarly, span of sine x and cosine x is all functions of the form a sine x plus b cosine x, where a and b are real numbers. So span just means all possible linear combinations of these things. All expressions that are multiple of this plus multiple of that plus multiple of a third thing if there is a third thing. If we look at in the space R bracket X of polynomials in X, span of 1x, x squared, x cubed is all the things you can take by taking all the things you can get by taking multiple of 1 plus multiple of x plus multiple of x squared plus multiple of x cubed. So that's all the polynomials of the form a plus bx plus cx squared plus dx cubed, which is all polynomials of degree less than or equal to 3. These multiples could be 0. D could be 0. So we don't know that the polynomial has degree exactly 3, but has degree at most 3. So polynomials of degree less than or equal to 3. Now sometimes the span of certain elements in the vector space doesn't have a nice name, like the upper triangular matrices or the polynomials of degree less than or equal to 3. So for example, if we look at the polynomials again, if we look at the span of 1 plus x and x plus x squared, so all the polynomials you can get by taking multiple of 1 plus x plus multiple of x plus x squared. So it's all the things of the form a plus ax plus bx plus bx squared. Where a and b are real. And I think the best way to write that is just all the polynomials of the form a plus bx plus bx squared, where a and b are real. I can't think of a nicer expression for that, so that'll just have to be our best description of what that space is. Similarly, in R3, I could name two vectors. The span of the vectors 1, 0, 2, 1, negative 1, 1 is all the things we can get by taking multiple of the first plus multiple of the second. Something like S 1, 0, 2 plus T 1, negative 1, 1, where S and T are real. And we could combine these into one vector expression and say this is all the things of the form S plus T negative T 2S plus T, where S and T are real numbers. Just a slightly condensed form of what we wrote earlier. The end.